The term black hole is in surprisingly common parlance for something that you can't actually see with your own eyes. Black holes have a reputation for sucking in everything, and they get the blame for that piece of homework that we did honestly, or that report that can no longer be found. But I'd like to reassure you, I'm not going to be talking about administrative black holes today, solely astrophysical ones, the ones that we actually find in outer space, the ones that we observe with telescopes. So I would like to emphasize at the start of my talk that black holes are a thing. They are real and they are out there. They are part of science fact, not merely fiction. The original thinking for black holes significantly predates Albert Einstein. The initial thinking came from the Reverend John Mitchell in the late 18th century, shortly after the Franco-Prussian War. It was a time of relative peace and quiescence in England. And from his work, black holes were actually predicted by mathematics centuries before they were discovered by telescopes. The whole theoretical framework for this, the whole conceptual framework from this, came from pure thought by someone who was free to think. Well, what is a black hole? What is an astrophysical black hole? A black hole is a volume of space where the attraction due to gravity is so strong that nothing, not even light, can escape from it. As I mentioned, the Reverend John Mitchell, a rector of a parish up in Yorkshire some centuries ago, who was very, very keen on astronomy and geology and theology and magnetism, started pondering what would happen if you had a star that was so massive that its gravitational field would begin to affect the passage of light. Surely, he reasoned, there would come a point where you had exceeded a threshold and light would not be able to escape, and you would have what he termed a dark star. He published this in the Proceedings of the Royal Society in 1783. He had entirely accepted Isaac Newton's theory that light consists of small particles. And he reasoned that these particles, trying to emerge from the surface of a star, could be subject to gravity. Although there are aspects of this thinking that are out of date, we now think much more in terms of the curvature of space-time, he was on the right track. Too much gravity in too compact a space, and life would be very different from the kind of physical behavior that we are familiar with. Well, the law of the jungle says that if you want to escape a predator, you need to run very fast, specifically faster than whatever it is that is chasing you. The fastest land animal, an example of which is pictured here, is the cheetah. Well, the maximum speed with which it or any other mammal can travel depends on complex biochemical relationships that depend on the mass of the creature, its muscle strength, and its metabolism, and when it had its last meal. That can play out in two different ways. So if you want to avoid an unpleasant encounter with a cheetah, you need to be able to run faster than its maximum speed of 110 kilometers per hour, which translates to 30 meters per second. What about in outer space, and what about when we start thinking about how fast light travels? Well, light can travel 9 million times faster than a cheetah, so that's very fast indeed. But in order to understand this, and specifically in order to understand how this concept of being able to travel fast enough to escape from something impinges on our understanding of black holes, I thought we would start properly today with thinking about a little light rocket science. So, what happens if you want to propel a spacecraft so that it can escape from the gravitational pull of planet Earth? I have here a picture of the Sabre engine designed by Reaction Engines. Now, supposing this is propelling a spacecraft, and the aim is that that spacecraft can escape from Earth's pull. The people who design the spacecraft will be mindful of an important parameter in this field, which is known as the escape velocity. So the escape velocity is how fast you have to move away to escape from whatever it is you're trying to escape from, whether it's the gravitational pull of a planet or whether it's the cheetah chasing after you, hungry for its lunch. Well, if you want to escape from planet Earth's gravitational pull, and if you don't have any other propulsion, if you're not equipped with such an engine, you need to be able to travel at least 11 kilometers per second. I'm showing here a picture with, on the vertical axis, speed of launch of a particular spacecraft, and on the horizontal axis, the distance from the very center of planet Earth. The curve that I'm plotting tells us about the speed at which the rocket launching a satellite called Spitzer, which helps us with lots of infrared observations of outer space, how fast it was traveling according to the distance that it was away from Earth. If there were no propulsion, it would have to be traveling, initially starting from the center of Earth, which is at about 6,400 kilometers, it would need to be traveling at least 11 kilometers a second to escape the escape velocity, to exceed the escape velocity from Earth, which, as I said, is about 11 kilometers per second. That's 34 times the speed of sound. If you prefer it in different units still, that's 25,000 miles per hour. There are some different subtleties here because there is precisely an engine propelling the spacecraft away from planet Earth, but 11 kilometers per second is the speed that a spacecraft needs to be traveling if it is to escape the gravitational pull of our planet. So, supposing we want to escape something other than the rocky planet on which we live, how does escape velocity depend on relevant physical parameters? I'm going to show you an equation which encapsulates the behavior of escape velocity. And let me just tell you what some of these symbols mean. On the left, v escape is the property that we're after. How fast do you have to travel to escape from a mass, m kilograms or whatever units of mass we're using, if you're at a distance r away from the center of that mass? The symbol G there symbolizes Newton's gravitational constant. And if you haven't met that before, don't worry. All you need to know is that it is as constant as the number 2, which is also in that formula. The point is, the more massive the thing you're trying to escape from, the larger that capital M is, the greater the escape velocity that you need if you're going to be able to get away from its gravitational pull. If you're dealing with a very compact manifestation of that mass, if your distance from it is very small, encapsulated here by the letter R, if you're very close to the center of mass, then it is even harder to get away. You need a much faster escape speed. So let's consider an extreme situation where our capital M, our mass, is very, very large, and our distance away from the center of that mass is really quite small, making that escape velocity very large indeed. Let's put that thought together with something that we met in the first lecture in this series on cosmic concepts, the fact that there is a maximum speed limit in this universe corresponding to the speed of light. you can imagine that for some given mass, capital M, there is a distance r from it within which, if you were to try and escape, you would need to be travelling at a speed faster than the speed of light. But you know from the first lecture that you can't travel faster than the speed of light. So that distance r, which gives you a speed, an escape velocity, equal to the speed of light, defines a surface, a spherical surface centred on your compact mass, within which you can't escape from the interior, because if you were to do so, you would need to be travelling faster than the maximum speed you can travel at in the universe, the speed of light. It is seriously bad news to be inside the event horizon of some particular mass. The story will get worse as we go on. But just for illustration and to help calibrate, if our sun, which thankfully is giving us lots and lots of light, which means that photosynthesis can happen in plants and we can grow crops and we and animals can eat crops and thereby survive on this planet, if the sun suddenly stopped being a star, this won't happen, by the way, this is just a thought experiment, if the sun stopped being a star and collapsed down to a point, if you got within 3 kilometres of that point, you would be inside its event horizon and there would be no escape. So this business of the event horizon, which you can think of as a mathematical surface defined around the centre of a black hole, it implies an unavoidable physical reality of no escape. You can think of it as a one-way membrane. Outside of it, when you're at a larger r, a larger distance from the centre of that mass, if you can propel yourself sufficiently quickly, you can escape. As you get closer and closer to that event horizon, there is no escape unless you could travel at a speed approaching the maximum speed limit in this universe, the speed of light. It is very dangerous to get close to an event horizon. You have been warned. So what does happen to matter that gets near to a black hole? Well, if you consider the matter that passes through that one-way membrane into the event horizon, that's it. You're not going to learn about the characteristics of whatever matter it was that fell inside the event horizon once it's fallen in. Its history, you're going to learn nothing else about it. There is no escape from inside an event horizon because you cannot move fast enough. You are trapped forever. Now, in fact, in astrophysical situations where matter gets close, even too close to a black hole, it doesn't all get swallowed. In fact, black holes are very messy eaters, and typically, depending a little bit on how fast the matter is moving nearby the black hole, only 1/10 of it is typically swallowed under the normal sorts of circumstances that happen nearby black holes. Outside the event horizon of the black hole, however, it's very different. Matter can escape, matter will escape, but you see some very impressive fireworks at the same time. Just outside of the event horizon is still a place of extreme physical conditions. Not as extreme as inside the event horizon, of course, but certainly very extreme, and specifically not the kind of conditions that we could replicate here on Earth. And so that does mean that studying black holes, studying how matter behaves in the vicinity of black holes, is very fruitful for understanding the way that they distort space-time, and they enable us to test particular theories of physics, such as Einstein's general theory of relativity. I'll talk a little later on in the lecture about the kinds of fireworks that we get from outside of black holes. But first of all, I want us to consider, where are black holes? A good place to look for a black hole is where matter collects. And an excellent example of this is at the centre of a galaxy, at the centre of its potential well, where matter is collected in and sucked in. So we're going to start with home. We're going to think about our own galaxy, the Milky Way, and I want to draw your attention to its centre, the galactic centre. Just to help orient you, I would mention that we are over here to the left. We're something like 26,000 light years away from the centre of our galaxy. So if we could travel at this very fast speed of light, which unfortunately we can't, it would still take us 26,000 years to travel there. So this is the place that we are going to focus on. And I want to mention the work of two particular teams, one based in Germany and one based in California, who independently studied the activity at the very centre of our galaxy to try and find out what was at the centre of our galaxy. So the German group, Reinhard Genzel et al., took successive images of the centre of our galaxy at infrared wavelengths so that the radiation could pass through all the dust that typically gathers towards the centre of our galaxy. And in these successive images, we're able to trace the ones near the centre that were moving. This was done over the course of about a decade, and it was done similarly in California, completely independently, by a team led by Andrea Ghez. The American one is in colour. And you can see that in the successive images are plotted, the positions observed from successive images, which trace out the paths, the trajectories of the orbits of these particular stars around something at the very central galactic point indicated by that yellow star in the middle. So by making these time-lapse images and observing change, they were able to see the orbits of these stars, knowing what types of stars they are and what masses they had. They were able to solve for all of these orbital parameters and then calculate what was the mass of the lightless yet gravitationally strong entity at the location of that yellow star there. And both groups independently found that at the very centre of our galaxy, there is a black hole whose mass is getting on for 4 million times the mass of our sun. Its event horizon is something like 10 million kilometres. So matter that gets close to 10 million kilometres, which may sound large, but remembering we're talking about space, so that's way inside the symbol size of that yellow star on my previous slide, any matter that gets too close would never escape. So that's inside our own galaxy. Well, how is it that we would expect to see any fireworks at all from around near black holes? How is it that the astrophysical black holes, unlike the administrative black holes that I said I probably wouldn't mention, how is it that they don't just suck matter in? How is it that we get fireworks at all? Given that we know gravity is always attractive, whether you're talking about the tree from Isaac Newton's apple tree being attracted to the ground, or the moon being attracted to the Earth as they orbit one another, surely, if gravity is always attractive, and if black holes are the origin of a very strong gravitational attractive field, how come black holes don't just suck in matter without any trace whatsoever? It's very important to realise that the law of gravitational attraction, which is one of the laws of physics, is not the only law of physics at play. Another very important law of physics, which is ongoing at the same time whether we like it or not, is something which is known by the name of the law of conservation of angular momentum. If angular momentum isn't a term that you've met previously, worry not. Just imagine that it's a property of something orbiting around the mass that you're thinking of, be it a planet or a black hole. However fast that matter is spinning, if you try and make it spin and orbit more closely, it will go faster and faster. If you try and make it orbit further away, then that orbiting will take place more slowly. That property is angular momentum, and it's a conserved quantity. So if you try and push things too close, they will start spinning faster and faster and faster. That's angular momentum. It is a conserved quantity in physics. So at the same time that matter is being sucked in towards the black hole, it is spinning faster and faster and faster as it gets sucked towards it. These laws of physics are happening at the same time in combination with one another. And it's that concerted action, that combination of physical laws, that gives rise to very, very rich phenomena and indeed fireworks. So if we want to understand how black holes react when matter comes nearby, it's good to look at some nearby examples. And later in my talk, I will be talking about some examples in our own galaxy. But I want to show you an illustration to start with, describing the kinds of situations that can arise. So the big white sphere, think of that as being a normal star, much like our own sun. And imagine that at the very centre of this red disk, you've got a black hole, which is gravitationally sucking matter, pillaging matter from that normal star. They're orbiting one another because typically when stars approach or a star approaches a black hole, they're not approaching head-on. If they're approaching at all off-axis, they will start orbiting one another. The black hole will start ripping, sucking material away from the normal star. Because of this conserved quantity of angular momentum, it will spiral in towards the black hole in a holding pattern, a bit like the kind of pattern that you follow when you're a plane orbiting at Heathrow waiting to land. Angular momentum is conserved in the case of this holding pattern. We call it an accretion disk. And what happens next, whether or not the matter gets sucked in and swallowed by the black hole, which happens to say 10% of the matter, or whether the matter gets thrown out and spat out well away from the black hole, projected miles away, thousands of light years away, in fact, into outer space, that depends very much on the detailed physics as you get closer and closer to the black hole. So this is obviously just a cartoon, but it's a cartoon representation of an accretion disk, a spiraling pattern of matter getting closer and closer to that black hole, which is going to become important for our story later on. Let me make the point that the event horizon that I referred to a few moments ago is a very, very tiny, minuscule dot well within the centre of that cartoon disk structure that is illustrated here. So let me just take you back to outside of our own galaxy. I showed you this optical image in the very first lecture of the Cygnus constellation of the northern sky. And I showed you when I zoomed in on the very centre that what may initially look like it's just another one of those stars is in fact, when sufficiently zoomed in, a big galaxy all on its own, quite some considerable distance from our own galaxy. And I drew your attention to the fact that while this is the optical view of that part of the night sky, if we look at radio wavelengths of the exact same bit of the night sky, but using a radio telescope, observing at wavelengths about this long, we see a very different picture, a very, very different picture, characterized by these two dumbbells of radio-emitting plasma, which are fed from the very central point, which is coincident with a supermassive black hole. This is a very large structure indeed. It's projected here on the same scale as the previous optical image. But whichever way you look at it, it is large. From one end to the other, the length exceeds 100,000 light years. A light year being the distance travelled by a ray of light in 1 year. And for this structure to grow to the size that it is, takes in excess of 1 million years. This is not, my friends, amenable to human observation. Please God, we might live for several tens of years, or perhaps even 100 years. There's no way that if that's the human lifespan, we can hope to be able to observe how this kind of object evolves, how its jets are initially launched from the vicinity of its black hole in the very middle there. But this is a prevalent kind of phenomenon throughout space. A great many gigantic galaxies have similar sorts of structures wherever we look in space, be it near or be it very, very distant on the other side of the observable universe. Such objects are everywhere. I also showed you in my first lecture an image of this beautiful radio galaxy, similar to the galaxy in Cygnus that I showed you earlier. Slightly different structure, entirely coincidentally with having its prominent jets going from left to right. That is a coincidence. This beautiful radio image was made by Fraser Owen and his co-workers at the US National Radio Observatory. Now, if we zoom out and do a very wide-angle view of this same bit of the radio sky, we see this very large structure, over 500,000 light years in extent from top to bottom. Believe me, this entire structure, 500,000 light years in extent, came from the activity that goes on just outside the event horizon surrounding the black hole at the very center of the action in this object. Just as it does in a great many other objects in outer space. So I'm just going to zoom in here and hopefully give you a sense of just how far we can zoom in. These are some of the, until earlier this year, these were some of the finest, most detailed observations that could be made of this structure. Well within the central point that the plasma is flowing away from is the accretion disk, that swirling pattern of matter. Actually, it's in an orientation more perpendicular to the plane of the screen, and well within inside that is the event horizon of the black hole that is giving rise to these exotic phenomena of matter being spun out and spat out away from its vicinity because it can't spin fast enough to actually be sucked in because of the maximum speed of light. Well, since April of this year, 2019, it's been possible to go in even closer to the black hole that gives rise to the launch of these jets, and I just want to briefly tell you about that. This is some work done by the Event Horizon Telescope team. They combined signals from telescopes in a number of different nations. Technically, this was an incredible undertaking to be able to combine these radio signals and zoom in to such a tiny fraction of a pixel in that central dot in my previous slide that they were able to image for the very first time the silhouette of the event horizon at the heart of that object that gives rise to that amazing radio structure over 500,000 light years in extent. despite the fact that the event horizon of a black hole is, relative to the structures that we're talking about, not that large, its influence over outer space is tremendous. And in particular, when you get these huge radio structures, they contain so much energy and so much heat that they can help reshape a galaxy as it's collapsing and forming for itself. So it's important to understand how these jets are launched, because then we are on the way to understanding how the formation of structure in the universe is influenced. Truly, these jets of plasma squirted from the vicinity of the event horizons of the black holes, outside of the event horizons of the black holes, are everywhere in the universe, and they give rise to some big questions in current astrophysics research, like how do they launch? How can they escape from nearby the black hole? Well, I indicated that these extragalactic quasars and radio galaxies can take, for example, 1 million years or 100 million years to grow to the extents that we see them in outer space. It is much more fruitful, therefore, to see if there are any speeded up, scaled models of these kind of objects in our own galaxy, that maybe we can study the same physics but a bit speeded up over and above the million-year timescale that some of these objects take to grow to the shapes and sizes that they are. So let's now return to our own galaxy, the Milky Way. And this image is of our Milky Way by night, taken from the garden of my colleague, Stephen Lee, who will feature later in our story. This image was taken just with a normal DSLR camera in the dark skies of rural Australia. Now, I want to zoom in over on the left, and if you see those red circles just there, I'm going to zoom in to that region of the night sky and show you an image of what we could see if our eyes could observe at radio wavelengths. Again, we don't just see stars, we see a very different picture. This is not a simulation. This is a real image from the Very Large Array Radio Telescope, affectionately known as the VLA, in the southwest United States, that I made some years ago. And this is a higher resolution zoomed image of the exact same object. Jets, again, emerging from very central location, which we believe to be a black hole whose mass is something like 20 times the mass of our sun. Vastly smaller than the black holes in M87 and in Cygnus A that I spoke of earlier, whose masses are something like 1 billion times the mass of our sun. This object has a black hole whose mass is about 20 times the mass of our sun. And lighter weight here means more rapid dynamical timescales. Things that are lower mass you can think of as being more nimble and evolving much more rapidly than the much more massive versions of the same phenomenon. You may notice that there's something of a zigzag curly corkscrew shape of this radio structure in the night sky. That's for real. Your eyes are not deceiving you. It really is zigzaggy on the left and curly corkscrew on the right. We believe that this arises because as these oppositely directed jets of matter are squirted away from near the black hole, outside the event horizon, from the accretion disk, the direction along which they are launched precesses through space, tracing out a cone. I don't know if any of you have paddled a kayak, but the shape traced out by my arms now is much like the shape of the paddle of a kayakist in the rest frame of the kayak. That's exactly what this object is doing for real. What's the timescale for this? believe it or not, it's about 6 months. And closer within, on very fine scales, we see this object to vary not just on timescales of 6 months, or weeks, or days, or hours, but even faster than that. This is a beautiful image, and this set me doing a whole lot of research on this object in particular and these phenomena in general. One of the things that you would really love to know is the speeds and the angles at which material is spun out and spat out from near a black hole. These radio images are beautiful and wonderful and rich in information, but they don't tell you about direction, and only indirectly do they tell you about speed. So we have to get clever. We have to make simulations, we have to make calculations, and there are some other observations that we can do. But let me show you a cartoon before I show you some other kinds of observations. So what I'm showing you now is a cartoon movie of what the object in my previous slide, which is a type of object known as a microquasar, would look like if I could hijack the Very Large Array radio telescope round the clock for 6 months, which I wouldn't be allowed to because other professionals want to use the time for their research projects as well, and if I could colour code the material launched from the black hole, the colour blue if it's coming towards Earth, and red if it's going away from Earth. This cartoon movie shows you exactly what you would expect if you did indeed have plasma being oppositely directed from the vicinity of a black hole, squirted along an axis which precesses in space, if that plasma is travelling at a speed comparable with the speed of light, in this case something like 1/4 of the speed of light. In case anyone's feeling a little bit hypnotized by that image, sorry, let me show you a slightly different movie, which some people find a little bit easier to take in. Imagine that you've got pairs of bolids of plasma launched ballistically from near the black hole, ballistically meaning they're not decelerated or accelerated as they fly away. They are launched and they trace out because of this changing direction and because of aberration effects associated with the speed at which the plasma is travelling. We see this amazing structure from a black hole. So if one wants to study, and I do, how matter behaves near a black hole and how it is launched from near a black hole, it's necessary to use techniques other than radio astronomy to start getting down to some of the detailed astrophysical processes that are at play. So I want you to imagine from the very central launch point that you point not a radio telescope, but an optical telescope, and that optical telescope is equipped with a clever bit of instrumentation called a spectrograph, which splits up light, starlight, into a spectrum in much the same way that raindrops in a cloud split up sunlight into a rainbow. So this is an example of such a spectrum. And I just want to briefly take you through what we're really seeing here. That very strong peak is known as an emission line, the green one in the middle, and that corresponds to hydrogen gas that's being sucked in towards the black hole, spiraling around it, and orbiting at greater distances, about to be sucked into nearby the black hole. The blue line is still hydrogen gas, but it is light from plasma that is moving towards the Earth. The black hole has launched it towards the Earth, and so the light that we see from it is blue shifted to shorter wavelengths via the Doppler effect that I mentioned in my previous lecture. This red emission line is the same version of that, but in the opposite direction, the plasma that's being launched away from Earth. Realizing that if I pointed an optical telescope with appropriate instrumentation at the very middle, the centre of activity of this black hole, led me to set up a research project which I'm going to briefly describe to you, which is called the Global Jet Watch. This is a globally distributed project designed to investigate the successive attraction and expulsion of matter from near black holes. As I indicated, some of these phenomena take place on timescales of hours and days. Now, the difficulty with doing optical astronomy during the daytime is that you can't. It's not just a difficulty, it's an impossibility. If our sun is above the horizon, then sunlight will completely swamp out light from all the other stars, and so we can't study them. So if you can only do optical astronomy at night, but you want to study phenomena that are evolving on sub-24-hour timescales, you need a distribution of telescopes which is separated in longitude so that you've always got one of them in nighttime, in darkness, so you can do astronomy. Imagine that we're looking at a target over there on the left. As the planet rotates, then each observatory at a different longitude can take it in turns to observe an evolving phenomenon, such as the one I described around this changing microquasar in our galaxy. Well, I set up observatories in these different places with the help of a number of colleagues and a number of people. How do you set up multi-longitude telescopes around the planet? It's the gritty business of lots of concrete, lots of spanners, lots of ladders. But when you get there, you get a beautiful view. This is of the southern night sky above the telescope that's in Chile. This picture here is of the structure of the top end of the telescope in Chile. And this is the back end of one of these telescopes showing our various pieces of instrumentation which can either take images of the night sky with the camera at the top, or when we divert the light path to go to the left into a fibre optic cable, we are able to take spectra, rainbows of the phenomena that I've been describing. Here is a side-on view of the telescope, and down at the bottom is the crucial piece of instrumentation, the spectrograph, which gives us the spectra of these phenomena. At the heart of this instrument is a dispersing element known as a volume phase holographic grating. Don't worry if you don't know what that means, but this is analogous to the drops of water in the rainbow that disperse the light according to colour or wavelength. Each of our observatories is equipped with one of these spectrographs. They were designed by my colleague, Steve Lee, who has worked at Australia's largest telescope for many years, the Anglo-Australian Telescope. And we have built up and commissioned this instrumentation at all of our observatories. Here is a picture of our observatory in Western Australia, which was created thanks to a very generous donation from Derek Benham, whose birthday it would have been today. This shows you all 5 of the telescopes, some of them in nighttime, some of them in daytime. And all 5 of these give us data streams via spectroscopy for our astrophysical research programs. Before I take you back to some of that, I'd like to share with you a few spin-offs of this research program. The original 4 observatories in the Global Jet Watch were located by design in residential schools. I wanted to do my bit to encourage the next generation of budding young scientists, particularly in countries that do not traditionally think of females as scientists and engineers. These are some of the girls at our observatory at the school in South Africa. Before local bedtime, they are free to operate the telescopes for themselves, and I do encourage them to play, because it's my observation that when teenagers are having fun, they're in a place where they can learn. And I want them to learn skills, not merely be spectators in this activity. These are some of the girls at the India School Observatory. And by night, as I say, they can explore craters of the moon for themselves. I've never encountered the thirst for knowledge at this residential school in rural southern India anywhere in the world. They are so thrilled to have the opportunity and the privilege of a formal education. Over 50% of these students are first-generation literates. They get to play with a shiny telescope and become familiar with technology, and they are very accomplished at it. Sometimes I connect with the schools over Skype, and there is a huge amount of fun to be had at the same time as learning. Before going back to astrophysics, I just want to share with you an email I got from one of the students at the India School one day. Dear Madam, I hope you saw the image of Jupiter. It was magnificent. We even saw, this is a list of other interesting objects in the night sky, and many more. Guess what, Madam? Each night in my dream, I play only with stars and nebulas. Once I enter the observatory, I forget everything. I feel I have entered heaven. So there is an important spin-off from this project with what I hope are tomorrow's scientists. After local bedtime, these telescopes are operated over the internet and we haul in data. I will just briefly mention, however, that our India School Observatory, pictured on top of the school roof here, is entirely powered by our nearest star. This is because the electricity in that part of the world is so camera-fryingly bad that it was necessary to use solar power. This is the horse that delivered the steel with which we built a shed to install the solar electricity, installed with my colleagues Chris McCarridge and Steve Lee, both from the Anglo-Australian Telescope. We store 2,000 amp hours of energy, and we collect the light with panels that are up on the school roof, just facing opposite the observatory. And it is a powerful exemplar, I think, to the students at this school to realise that once you've commissioned and installed your solar farm, you're set. You can get energy thereafter from the sky for free. But back to astrophysics data, which is what inspired this project. I mentioned that an optical spectrum, a single optical spectrum, tells us about the material that's launched towards Earth and away from Earth. And at the same time, that central peak tells us about the material as it's being sucked in and attracted in. And as expected, every time we observe, the spectra looks different. There are calculations that we can do based on where the position of the blue-shifted and the simultaneously measured red-shifted peak is in our succession of time-lapse spectroscopy that enable us to calculate the velocity at launch of the plasma that comprises these zigzag curly corkscrew jets that I illustrated earlier. Specifically, with these data streams, if you collect data for, say, a year, from spectra from all the different observatories, you can calculate, as we did, to make a prediction of what you expect the jet trace to look like on a particular date in the future, given a certain time of flight, having calculated the speed at which the plasma is moving in certain directions. This was our prediction for what the jet trace would look like if we could observe it with a radio telescope at a particular date. So we managed to get time on a particular radio telescope, this time the ALMA telescope in northern Chile. Despite a big earthquake that caused quite a bit of damage to our own telescope in Chile shortly before our observations, we all survived, thankfully, and with data from this radio telescope in combination with our prediction of what this object would look like the epoch that we would take the observation with the radio telescope, we made a prediction that showed our calculations were consistent with what the data from the ALMA radio telescope looked like. We were very, very pleased indeed at this confirmation, because we want to put together our understanding of the way in which the jet plasma is launched away from the black hole, with details of the calculations that I don't have time to present this morning of the matter that's being sucked in towards the black hole, whose dynamical signatures are encoded in that great big tall green peak in each and every optical spectrum that we collect. This is a dream come true for me, to be able to collect these astrophysical data at the same time as encouraging and engaging the next generation into science. Well, what are the benefits of studying black holes? Is it just an eclectic activity that has no relevance to any other aspect of life? I'd like to strongly make the case that it is not. As I indicated earlier, the vicinity of a black hole, where you have incredibly compact mass giving rise to a very extreme gravitational attraction, space-time itself is influenced by the presence of that mass. Space-time is curved. That influences the way that the light travels and the way the matter behaves. We cannot hope to replicate those extreme physical conditions here on Earth. By studying black holes, at a safe distance, I hasten to add, we are able to study regions of physics parameter space that would not otherwise be possible. And this is important for understanding the physics of the universe. It's also, as I indicated earlier, important to study black holes and the way they interact with matter and the way they eject matter if we want to understand cosmic history. If we want to understand how these structures grow and develop and redistribute energy and heat at much, much greater distances than you might ever imagine on the basis of the event horizon surrounding the black hole itself. But there's something else I'd like to mention as well, relating to the pursuit of the study of black holes, which I would guess has affected the vast majority of people in this audience today. Anyone who has connected to the internet today, I strongly suspect that you would have done so using Wi-Fi, using the 802.11 protocol. The fact that we can connect via the 802.11 Wi-Fi protocol arises because of the work of John O'Sullivan and colleagues at CSIRO in Australia in pursuit of an investigation to study a particular signature of merging black holes suggested by our Astronomer Royal, Lord Martin Rees, and Ron Eakers, an Australian radio astrophysicist. They wanted to investigate and observe a particular signature, and John O'Sullivan and his team worked extremely hard and extremely effectively on clever interference suppression algorithms, which they realized had tremendous potential for the communication that many of us benefit from today. So is it the case that black holes sucking in any and every material that come nearby them is the end of the matter? We've gone way beyond proof of concept. We've gone way beyond mathematical conjecture and prediction. And while we can never know the details of the matter that has fallen inside of the event horizon of a black hole, because it can't travel fast enough to escape, and so we can get no information from that matter to reach our telescopes, nonetheless, the majority of matter is not sucked in, but is spat out and redistributed by black holes. And so as far as astrophysical research is concerned, we are nowhere near the end of the matter. Thank you.